Yeah, so now we have Professor Pradipta Ghosh from IIT Delhi, and he mostly works on the collider phenomenology on supersymmetric models and also on the neutrinos in the neutrino sector in SUSY. So today he is going to talk about the neutrinos in the SUSY sector. And with that, I request or welcome you to deliver this talk. Please go ahead. Professor Ghosh.
So, thank you very much for this. Just 1 minute, let me just turn on the record. So, thank you very much, especially to the session chair and also to the organizer for the kind invitation and for the nice introduction. So, today I'm going to talk about neutrinos in SUSY. Now, honestly, talking about neutrinos in SUSY in a given duration is like fitting an elephant in the matchbox. I hope I'm clearly audible.
Hello? Very much.
Yeah, thank you. So the plan of this talk is like that. So I will just introduce a little bit about how we can actually generate neutrino masses in non-SUSY model, and eventually I will go to the supersymmetry. And also apology in advance, like in case if I miss any relevant references. I tried my level best to be as rigorous as possible, but at least for all the initial words. But if I missed your reference, sorry for that. So how we can generate neutrino masses? Of course, neutrino masses, as we know, as of now, this is probably the only confirmed and convincing evidence of the physics beyond the standard model. So, of course, when Glashow, Weinberg, and Salam, they formulated the standard model, I mean, there was no idea about the neutrino masses, but now we know. In fact, the 2015 Nobel was awarded for that. So the simple most possibility of generating neutrino mass is just like the way you can generate masses for the up sector in the standard model. You simply add right-handed neutrinos. So of course, then you are going to get the neutrino, the Dirac neutrino masses, which goes like, as I wrote here, MD is equal to the constant Yuka couplings times the wave. But of course, the price that you need to pay here, that if you want to satisfy the global 3-flavor neutrino data, first of all, you need 3 generations of right-handed neutrinos, and more importantly, if you want to fit the size of the neutrino mass, that is of the order of 0.1 electron volt, you need to consider a neutrino Yuka couplings, which is very small. So it is going to augment the kind of flavor puzzle in the standard model. The other option is, of course, you can add y is equal to 2 and SU2 triplet Higgs, which is carrying hypercharge of 2. And you can again generate the 3-level neutrino mass. But the problem is that if you want to make this particular term invariant under the lepton number, then of course, either you need to assign some lepton charges to this doublet, and whenever it is going to get a vacuum expectation value, so the lepton number will be continuously broken, and it is going to give rise to this infamous doublet Myron problem, which is experimentally ruled out. So either you assign the explicit lepton number breaking so that you have not the problem of the Myron emission, but then you are going to get problem that the wave is going to be of the size of only a few GeV. If I'm not making a mistake, then of the order of 8 GeV or so, which is very, very small compared to the 246 GeV wave of the standard model Higgs. So basically, and it is strongly constant from the rho parameter measurement. So moving ahead, the simple most solution to the other possible thing, which I will say that not the normalizable interaction, but through the non-denormalizer interaction using the dimension 5 Weinberg operators. So the first option is to use either a right-handed neutrino or any singlet. And as you can see, I have shown it diagrammatically that here, how you can generate a tiny neutrino masses. So this is a seesaw mechanism. So the heaviness in the scale of this ms, which is either the mass of the singlets or the right-handed neutrino, you can actually assure a tiny neutrino masses. So here, either you are violating the lepton number by 1 unit at 2 vertices, or you are violating the delta L is equal to 2 directly, that is the Majumdar mass term for the right-handed neutrino. Of course, you need to address the question that how to generate a Majumdar mass term. So either you just put it by hand, or you have to associate some new kind of symmetry, some new kind of U1X symmetry, but then you are going to end up with a richer collider phenomenology with additional Higgses and Z prime. So the other possibility is that you add a SU2 scalar triplet, and this is known as the type 2 SISA mechanism, as I showed here. So, and the concerned neutrino mass formula is given here. And similarly, just like a scalar triplet, you can consider a SU2L triplet fermion, and then you are going to end up with something that is known as the type 2 SISO mechanism. So these are the three primary kind of SISO mechanisms which are relevant for today's talk. Of course, there are much more complicated things. You have the inverse SISO mechanism, the linear SISO, double SISO, and things like the radiative mass model, like the Z-Babu model and something like that, which I'm not going to cover. So now, the straightforward way to discuss neutrinos about the supersymmetry, supersymmetrization of all this idea. So the first thing is that you just add a right-handed neutrino along with your MSSM. So if you do that, that is how you are going to generate the neutrino masses by the SISO mechanism. But the problem is that the moment you turn on this tiny Yukawa coupling, it is going to trigger the flavor violation processes through the lepton mixing. So here is a schematic plot of the branching ratio of the mu 2 gamma, a very well-known Charles-Lepton flavor violating process, and there's the plot against the seesaw scale. So as you can see, there are two limits: one for the situation before the double chew and the Reno, that is with the zero angle for the reactor mixing angle, that is theta 1,3 for the neutrinos, and the other is 6 degree, and we know that the current 3 sigma limit is in the ballpark of 8 degree. So you can see that the main problem of this kind of model, first of all, that the current mu 2 gamma sensitivity is of the order of 10 to the power minus 4. But the problem is that you can see the associated seesaw scale is too high, so it is very difficult to probe it at the collider. Of course, you have the other possibility. You can actually consider the TIFR scale seesaw, where the Yukawa couplings are of the order of 10 to the power minus 6 and 7, and that is going to give you a MR of the order of 10 to the power 3 GeV or so. So that is something that you can verify at the collider. But the problem of this is that, say, if you consider only one generations of the neutrino, you are going to end up with only one tree level mass. And if you would like to reduce the minimal number of new parameter over the MSSM, then you can go with I is equal to 1. That is one generation of the right-handed neutrino. But then, of course, you need to switch on the flavor, the loop effects, and that is the well-known example of the Grossman-Heber loop, which was also independently studied by other groups, where you can see that you introduce a Chinese neutrino mass splitting through the left-right mixing with the right-handed neutrino. And that's why this splitting is actually proportional to 1 by MR, that is the scale of the right-handed neutrino. So clearly, if your right-handed mass is too high, then they are practically of the same order, and you're going to get negligible contribution from the loop effect, just like the MSSM. But if you consider a moderate value of the MR, you are going to get a sizable loop effect. So moving forward, you can do the same for the type 2 seesaw. I'm not going to spend too much time, but here the only difference compared to the non-SUSY version is that because it's a supersymmetric theory, you need to assure your anomaly cancellation. So you need to have two pair of SU2L triplet. So hypercharge y is equal to plus minus 1. And this model, as you can see, that this is also going to give you some flavor violating process, which is we can relate with the mass of the triplet hits. And this M15 is nothing but it is how actually it is. I mean, it can be embedded in the grand unified theory. So this is actually coming from the 15 plate. And also you can see some nice correlation between the mass of this triplet and certain flavor violating branching ratios in the context of the Stau decay, the second Stau decay. So when you have knowledge about the neutrino mixing parameter, by using that, you can actually try to fix YT, which is roughly given as the ratio of the MT by lambda U. So if you try to do the same things in the context of the type 3 seesaw, of course, you can do that. Of course, then the underlying superpotential is a little bit complicated. So things are actually coming from the 24th plate of SU5. And under certain assumption, like if you assume that the boundary condition that you are using even at the width scale, they're of the similar order of the grand unified theory scale, then you can actually write down a simplified formula involving the triplet Gagino mass. And because this we know they are in triplet, so this is something that resembles the type 3 seesaw. And this YW, this is actually the coupling between the Higgs superfield, the Wiener superfield, and the lepton superfield. And again, in this case, the lepton violations, the flavor violating processes, this is triggered by this non-zero Yukawa coupling, so which is associated with this Higgs, the uptype Higgs, the Bino-Vino, or the lepton superfield. And once again, you are going to get CLFB processes, and you can actually, interestingly, particularly these things, you can either realize some of the flavor violating branching processes as shown by the plot in the right-hand side with some of the SUSY parameters, so M-half in this context, or you can actually have a nice correlation between the flavor violating processes, the CLFB processes, that is Li going to Lj gamma, with the neutrino mixing angle. The importance about all these processes is that here the flavor violation is triggered by the newly introduced Yukawa coupling. So whatever processes that you are going to get at the end of the day, be it in the context of the CLFB or collider signatures, they're actually determined by a terms of a few new parameters. That is the reasons, you can expect nice kind of correlations at the collider or at the CLFB experiment with the neutrino mixing angle and other SUSY parameters. So it actually opens up the revenue of the complementary searches. So just to complete the story, there is also another option, but now I am actually in the supersymmetric ligates. So this is one nice example of the supersymmetric inverse seesaw. And here you can see that here I am violating the lepton number by 2 units just by assigning certain lepton number to the right-handed neutrino superfield, and which is denoted by NC. Sorry for the change of notation for the sake of the convenience, and the pure singlet superfield. So that is S. So here actually the lepton number violation is actually by 2 units. So why it is called inverse seesaw? Because here you can see that the smallness of the neutrino mass is not really related to how large your seesaw scale is, but rather it is actually directly related to the breaking scale of the lepton number. So because of the explicit lepton number violation, you are not going to get things like the doublet Majoran and problem like that. So this is a kind of nice situation. But once again, you can probe this, you can investigate the kind of complementary aspect of this particular model when you compare certain, and you can observe certain correlation between the flavor violating processes with the neutrino mixing angle. Of course, you can actually extend it further, and you can also have nice collider signatures. For example, here actually we have explored one trilepton signal, and you can see that they actually, the ratio of certain collider signals, they actually show very nice correlation with the neutrino mixing angle, in this case, the atmospheric mixing angle. Of course, in this case, if you consider only one generation of the singlets and the right-handed neutrino, it is hard to explain, to satisfy the 3 flavor global neutrino data at the tree level, so you need to turn on the loop correction. So now I'm go to the kingdom of the something which is purely generic to supersymmetry, that is the kingdom of the apparative violation. So apparate is defined like that, and you can see that all the standard model particles, they have their apparity as +1, but for all the SUSY particles, their apparity is -1. So if apparity is conserved, that means the light is supersymmetric particle, as already discussed in the morning by Professor Vipati, so it is stable. So good thing about apparative violation is that you can get a pure supersymmetric origin of neutrino mass, and you can get new kind of collider signal, new signatures of the flavor violating processes, which are often way enhanced compared to the standard model predictions. And that actually offers a nice way to constrain the parameters, the new parameters. But the bad thing is that, you cannot use the lightest neutrino at the LSP, but there are ways to evade that thing. You can have new dark matter candidate. One of them is gravitino, as already discussed briefly in the morning by Professor Vempati. But now the big question is that, which kind of apparative violations, spontaneous or explicit? So first I'm going to discuss about the spontaneous violation. So that means the lepton number is broken when the left-handed neutrino or the singlets, they acquire waves, of course with the lepton number. So these are the 2 schematic diagrams, and you can see, you can see that whenever this neutrino, the left-handed neutrino is getting a wave, so you can actually have a neutrino mass like this. The good thing about this thing is that this is entirely supersymmetric, and because the lepton number, so now the interesting thing is that, again in this model, because everything is controlled by a few new elementary parameters. For example, in this context, either the wave of the right-handed neutrino or the wave of the left-handed neutrino. So once again, you can expect nice correlations between the neutrino mixing angle with, say, the right-handed neutrino mass or with the flavor violating processes. So these are like two candidate diagrams just to show these things. But this G is actually basically the Myron. So basically, if you actually you cannot really give a directly wave to the left-handed neutrino because that is once again going to trigger out this triplet Myron problem, but you can actually trigger a wave through the left-handed neutrino indirectly through the singlet wave as discussed by this gentleman long back. So in this case, because the Myron, of course, there will be a Myron that is a massless particle, but it will be predominantly of the singlet nature. So you can actually evade a lot of constraint coming from the collider or like Z decays. But once again, given the structure of the matrix, you will get only one mass at the 3 levels. So you need to go through the loop correction to satisfy the 3 flavor global neutrino data. But there is something really important, which was analyzed by Bhattacharya and Pearl back in 2010, that even if you start with the spontaneous Arfreddy violation parameter, especially when the right-handed neutrino, the scalar part of NC, it is actually getting a wave, you can generate effective trilinear and bilinear explicit Arfreddy violating terms as given by this tentative approximation. So although you started with a spontaneous Arfreddy violation, but there are ways to generate or to turn back the explicit Arfreddy violation term through this kind of nice diagram. So this is a very nice article. I mean, of course, I don't have time to cover all the details. So moving on, now we turn on the explicit Arfreddy violation. The simple most is actually using a term which looks like this. And you can see that this is exactly like the mu term as you all have seen this morning as it was introduced by Professor Vibhati. But you know that the only difference between the lepton superfield and the down type Higgs superfield is in terms of the lepton number. Their doublet structure, their hypercharge, everything remains the same. So you can easily replace them if you do not care about the lepton number at all. After all, if you think in the context of the standard model, lepton number is just an accidental symmetry. It is a consequence of the gauge invariance, the particle contents, and the renormalizability. But the problem that you have to face, that of course it is going to trigger a problem which is similar to the mu problem, because to satisfy the neutrino data, I mean, this parameter must be of the order of 10 to the power -4 or so, but that's the problem, that why it is actually so small. And these are the schematic diagram by which you can actually have an idea that how this epsilon parameter, either directly or together with the Gaugino seesaw, accompanied by the Bino and the Wino, which are a part of the neutralino. These are in the flavor basis. In the mass basis, as you have seen this morning, they are known as the neutralino. So eventually you will get a mass matrix like this, a generic master. But the problem of this is that this is, although if you actually consider all the 3 generations, this is a rank 1 matrix. So once again, you will get only non-zero masses at the 3 level. So you need loop correction. Now, the loop correction, it's a really, really tedious business. So there will be a lot of loop correction. So some of them are like the mu B, the BB, or some even more complicated. I don't want to go into the detail. I just actually have this slide for the sake of completeness. But there are something really important that these loop corrections are really useful to satisfy the 3 flavor global neutrino data, especially when even if you consider that the left-handed neutrino wave is 0 or the epsilon parameter is not there, you can trigger it back using the corresponding terms in the soft supersymmetry baking sector, which is the beta epsilon alpha, given that they are not aligned. That you can do. But the important thing is that not all loop is going to contribute to those neutrino masses which is 0 in the 3 level. For example, if you consider this loop, as you can see from my cursor, so this mu alpha and mu beta, this tilde, these are the generic representation of the neutrino mixing with the neutralinos. So, and here the dominant contribution is coming from the top stop loop because of the large top Yuka coupling. So here, this is going to contribute to that particular mass, which is already massive in the 3 level. whereas the remaining masses are coming from the other contribution, from the BB or MeB. So unless there is a miraculous cancellation between different Higgs contribution like H, capital H or A, that is the MSSM, the SM-like scalar, the true MSSM Higgs and the pseudo-scalar Higgs, typically it is the BB loop which dominates. Of course, you can have trilinear arbitrary violations. So that means now the terms are of the trilinear nature. And arbitrary violation, as if you can remember a few slides back, so it can appear either through the baryon number violation or through the Lepton number violation. The last number is actually the baryon number violation. So these are actually few schematic representation of the trilinear loop. So in the context of the trilinear coupling, it is always in loops. But you can also have mixed terms, which are a combination of the bilinear and the trilinear things. One important aspect about the trilinear terms is that sometimes you try to rotate the bilinear terms away from the superpotential, either to get rid of the epsilon problem or logic like that. But if you turn on the trilinear couplings, they can actually reproduce back the bilinear couplings, although there are other ways to get back the bilinear couplings through the subsector RG running. But even through the trilinear coupling, you can get back the bilinear terms by the loop contribution. Typically, these are these are severely constrained from other processes, as I will discuss soon. But the importance of studying neutrinos and the supersymmetries, especially in the context of the arbitrary violating models, is that it actually gives you, or it actually opens the avenue of the complementary searches. So you can correlate your observable from different experiments, neutrino to collider, charged lepton flavor violating process to neutrinos and things like that. So for example, here you can see that branching ratio of the, because as I mentioned that because of the arbitrary violation, the lightest supersymmetric particle is no longer stable, so it can decay. So these are some schematic diagram of the two body decays, and you can see there is a kind of correlation. And especially since the arbitrary violating parameters are very tiny in nature, have to be, because otherwise you cannot satisfy the tiny neutrino data as observed experimentally. So because of these parameters, the smallness of these parameters, this neutrino decay is typically long-lived. So they will produce some things which is an interesting signal for the BSM physics that is known as the displaced vertex. So before decaying, they can actually traverse the finite distance from the primary vertex of production, they go to the secondary vertex, and eventually they decay. So appearance of the displaced vertex is a nice experimental signature of these scenarios. And of course, you can have more interesting correlation between the flavor violating decays of the neutralino at the collider with the neutrino mixing angle. So these are like three schematic diagrams with the atmospheric mixing angles, the solar mixing angle, here with the model parameters, and with this U square E3. So this is actually one element of the PMNS matrix, and this is directly proportional to the reactor mixing angle. So I have actually plotted, so these red lines are the limit of the current 3 sigma data. So now you can see that if I am actually getting some points in this region from the collider searches, so then clearly I can have the right to say that this is not the correct model to fit the neutrino data. So this complementary analysis is something which is very important. So of course, as I mentioned, there are other searches also like CLFD processes. And there are also flavor violating Higgs decays. So if you turn on the trilinear couplings, you should be very, very careful because it can trigger some flavor violating decays even at the tree level. And that is why these couplings are really constrained. But there are more sectors which can actually help us to constrain these processes. For example, that is the example which Professor Vempati discussed in the morning, the proton decay. So you know the lifetime of the proton decay as per, I think, the supercommunicant latest search is of the order of more than 10 to the power 32 years. So if you consider the this couplings lambda or lambda prime of the order of 1, as Professor Vempati mentioned, then and with TeV scale SUSY partners, so you will have like 10 to the power minus 11 or 12 order of the lifetime. So which is not true. You can also, and another important example of this consequence of this trilinear coupling is that the generation of the neutronless double beta decay, so which is still a process, and that is one very important process to confirm the Majorana nature of the light neutrinos in an unambiguous way. Of course, it can lead to more interesting collider signature through this trilinear coupling. So that is why they are very interesting to study. like two same sign dilepton and two quark jets, or four same sign or four dileptons through this neutrino pair production. In fact, this particular diagram, a little modification of this diagram can also trigger flavor violating G decays, which is very important to search. And the current bounds, like for Z going to E mu, is of the order of 10 to the power minus 6 or so from the particle data group. And more importantly, the trilinear couplings, they were also very resourceful to explain very easily several hype excess, as we all have encountered in the recent past. For example, certain combination of this lambda 1-1 coupling can actually reproduce this much hype EEJJ excess, as we have seen during the 2014. And similarly, it can also reproduce this infamous 750 GeV diphoton excess by playing with the model parameter. And because of this couplings, the trilinear couplings, their flavor structure is so rich, they can also contribute to the flavor violating decays, like to BS to mu plus mu minus, and they can even contribute to muon G minus 2, which, as you know, that in hot topic after this recent FNAL reporting. So to end up the story, as I said, I have only covered a very few examples just to give you a brief overview of the things that what enormous potential lies in the supersymmetric model, especially with the operative violation that can accommodate the neutrino masses and can predict nice signatures at colliders, at flavor violating experiment, or in other connected sector. So these are some other models examples which can also generate neutrino masses at the supersymmetry. For example, you can go to the NMSSM model, where a solution of the mu problem is automatically provided through a dynamical origin. So in some of the models, you can have tree-level masses for more than one neutrinos, and because they are already NMSSM, so as already mentioned by Professor Vempati, so the related collider phenomenology was already richer in terms of the extra Higgses and extra neutralinos. But on top of that, if you turn on the operative violation or lepton number violation, then the associated phenomenology is even richer and even complex. So these are some of the articles where they actually propose these different kind of models, but this is only not even the tip of the iceberg. So to sum up the story, I tried my best to give you a brief overview of the neutrinos at supersymmetry, but it is my belief that the take-home message is that if you only focus on one of these things, I mean, who knows, maybe the S particles are really heavy. And if we're going to miss them even at the high luminosity LHC or with this 27 TeV or this 33 TeV proposed collider, then maybe the complementary searches is our only hope, which can help us to probe the kingdom of the BSM physics through indirect evidence. And for that, we must study everything together to have a broad overview and a better understanding of the BSM theories. So thank you, and that's all from my side.
Thank you so much again, Professor Ghosh, for this affluent and marvelous talk covering the neutrino sector in SUSY. Time for a couple of questions. Anybody? Students, no questions? Okay, so you already mentioned that it's more appropriate to look for the overall SUSY particles rather than the neutrino only.
No, because in my belief that this is the only thing that we have discovered and we have confirmed the origin as a BSM proof. Because dark matter, as of now, we have several excesses, but nothing confirmed.
Yeah. All right.
Yeah, one question. Can I ask one question?
Go ahead. Go ahead.
Yeah. So, Pradipta, is there any role of this extra terms that you added in SUSY models? What effect, or if any, they can have in beam physics?
Your voice was not very clear. Could you please repeat the question?
I will try.
We have some feedback, Ritesh.
Yeah. So basically, I was trying to ask, like, do you also have some of the observable of these extra terms in B physics?
So as you can see, so like BS2 mu plus mu minus. So through this trilinear couplings, you can actually constrain that.
Okay.
So this is just one of the kind of schematic diagram, but you can also do with the other processes.
Okay, so there are some like
yeah, I mean, you can of course correlate. I mean, you can try to constrain this new sector using the flavor violating or the data available from the flavor sector. But as you can see, that the main problem is that at least most of the time, what the experimentalists they are doing, because MSSM, even if I consider PMSSM, that is a theory with the 19 parameter. If I want to really explain my experimental observation in terms of the parameter, then 19, so that is the reason probably in spite of being severely constrained, CMSSM is still one of the I would say a hot favorite for the experimental to fit some new thing. Because it is too much new parameters. So unless you perform a dedicated and a statistical scan with proper meaning, it is very difficult to have something concrete.
That is true.
Because all the analysis that is
of course, you cannot do all the 19 parameters at a time. But what my question was, which you correctly answered, is that there exists a physical observer in flavor physics, which in a restricted manner can put constraint on this.
Exactly. Even most of the analysis appear, I mean, available from the ATLAS and CMS, they are actually only in the context of, I mean, they just believe that only a few arthritic violating couplings are turns on and the remainings are missing. So that is why they can actually constrain one or two of them. But if you actually turn on all of them, then it's going to be a mess. So, but such analysis, I believe, is required, but it requires an enormous amount of computation and also good collaboration between the theoretical and the experimental like scientists.
Yes, certainly.
You're welcome.
Thanks.
Any other questions? Anybody? If not, thank you so much again, Professor Ghosh, for this marvelous talk. And as you mentioned, that it's right time to have an experimental talk now. So thank you again.